Yeah, so absolutely. I've found Jim's work on the idea of Gaia hugely inspiring in my work in what's probably very mainstream climate modelling, especially in the Met Office half of my job, which is about looking at the potential future impacts of climate change. And I wanted to talk about two aspects in which I've been inspired by Jim's ideas in this area of work. One is the role of life in Earth system models and assessing predictions and projections of climate change impacts. And secondly, refers to the incident that Chris Rapley talked about yesterday when Jim visited the Hadley Centre and I brought down a whole set of my colleagues to sort of talk to him over 2 or 3 hours about our work. And as Chris said yesterday, Jim came away thinking that we were looking at a planet as if it wasn't the one we lived on. So I wanted to talk a bit more about how climate science is trying to think about actual impacts for people, but also expose still a lack of joined-up thinking, I think. So as we mentioned before, we are currently, under current emissions scenarios and policies, we're not on track to meet the Paris Agreement goals of staying well below 2 degrees and perhaps 1.5 degrees global warming. Current policies, according to the Climate Action Tracker tool by Climate Analytics, which looks at the implications of current policies, currently we're on track for warming of anywhere between 2.5 and 4.4 degrees Celsius global warming by the end of the century. Quite an uncertainty there because of the kind of challenge that Peter was talking about just now. We can't narrow it down, but it could be that if we're unlucky, we could be seeing perhaps 4 degrees global warming by the end of the century if sensitivity is at the higher end. So what does that mean for us? What would a 4-degree global warming world actually look like for patterns of climate across the world? And most importantly, what would that mean for us? Now, this is a complicated graph with lots of uncertainty, very confusing, and I've done that on purpose because trying to predict future climate is complicated, and it is confusing, and it is full of uncertainty. But basically this is trying to capture the range of projections of changing water resources in terms of river flow and runoff from a whole set of climate models currently used in the work by the Intergovernmental Panel on Climate Change, the IPCC. So there's about 30 models used here, and to try and do it in a nutshell, each of these pie charts shows the fraction of the models which show either an increase in river flow in blue or decrease in red for different levels of global warming at 1.5, 2 and 4 degrees global warming relative to pre-industrial for each major river basin. And the bars here show for 1.5, 2 and 4 degrees warming the range of results from these models. So blue being the wettest result, the greatest increase, red being the driest result, the greatest decrease. Obviously, I'm not expecting to look at every single one in detail, but the broad picture is you can see there's a lot of blue up here. There's a model consensus on generally going more towards increased river flows in northern Asia and eastern Asia, with some possibility of some decreases in some areas. Some areas, such as in the Mediterranean, Southern Africa, we're seeing, down here, we're seeing more of a consensus towards drier conditions. But in many areas, such as the Amazon, it's pretty much 50-50. We literally don't know whether the Amazon is going to get increased river flow or decreased river flow. Our own model in the Hadley Centre very famously predicted a drying climate, which translates into a decreased flow, but some models show an increase, and it could go either way. A lot of the uncertainty in this comes from the regional patterns of climate change. We can't tell for sure how certain regions will experience different patterns of wind flow, for example, although in the areas where there's high consensus, we're pretty sure that the high latitudes will see increased rainfall, hence the increased river flow here, and the Mediterranean region and Southern Africa will see decreased rainfall. So it's not just about model consensus, we understand the physical mechanisms behind that as well, which gives us more confidence. But in other areas, the jury is still out into the direction of change. But one important area to consider is, as I mentioned, the role of life in all this. So the role of the terrestrial biosphere in particular, and vegetation, and its role in the exchanges of water between the atmosphere and the land. So you've got precipitation as an input of water, water being returned to the atmosphere through evaporation from the surfaces of leaves and the soil and so on, and then transpiration, so evaporation through plants, through the microscopic pores in the leaves of plants, stomata. And that's a crucial part of the process. So they're all affected by weather and climate, so the amount of water in the atmosphere, the temperature, which drives evaporation. These things also affect weather and climate by returning moisture to the atmosphere and by affecting the cooling of the land surface. The vegetation is affected by the concentration of CO2 in the atmosphere, and that affects transpiration. Under higher CO2, many plant species reduce the opening of their stomatal apertures so they conserve more water, which means more water is retained in the soil moisture and more water is available for runoff. And that affects the global hydrological cycle and river flows. And we see that in the models, and we're also starting to see signals that this may be being picked up in the real world already as well. So this affects what we project for global land wetting or drying. This is now one particular projection, and here we're using the Earth System model, the Met Office Hadley Centre Earth System model, which includes the vegetation response to CO2, and we're looking at the percentage of global land projected to see a decrease in river flow. So less than 40% at 2 degrees is seeing decreased river flow, so more than 60% is seeing an increase in river flow. So it's more of a wetting world. And that increases slightly at a 4-degree world, so we go down to 35% decreased river flow, the rest with an increased river flow. So it's a wetter world getting slightly wetter as we increase global warming. But if we take the same meteorological outputs and use those to drive a standard hydrological model, which ignores the vegetation, which many hydrological models used for climate impact still do, we get the opposite. We see a drying world, more than 50% of the land with decreased river flows, and that gets even drier at 4 degrees. So the role of life in terms of the vegetation response to CO2 can change the sign of the response of the hydrological cycle. A drying world becomes a wetting world if you include the role of vegetation in response to CO2. What does this mean for people? I haven't got time to go into this in detail, but basically these days there are different pathways, different scenarios of how the future socioeconomic state may evolve over time. They're not predictions, but they're kind of narratives where the researchers that come up with these, they think about, is it a world of high population or low population growth, how the global economy may evolve. Could it be a world of a globalized world or a more kind of internally conflicted world? Two of the scenarios which are used for these things are called SSPs, or shared socioeconomic pathways. One of them, so-called SSP3, is a quite an unequal world. It has high population growth, it has some economic growth and moderate emissions, but it's a very kind of, they call it regional rivalry as a shorthand. So there's, it's sort of, inequality is quite high, as I say, and population growth is quite high. It's not a very rich world. On the other end of the scale, there's SSP5, as it's called, has a smaller but richer population. It's almost utopian in its vision because it imagines high inequality, so everyone is equally rich. But this all relies on fossil fuel emissions. So it's a fossil fuel, it's a recarbonised world, but with many, not so many people as in SSP3. And we can look at, say, one climate future, say one projected change in river flows around the world from the model I showed earlier. This is percentage change, by the way, I missed off the key. And then we can look at what the different human futures mean for water insecurity. So this is the SSP3, the poorer, more populated world. And this is SSP5, the richer, less populated world. And looking at the country level, whether the water insecurity has increased in the sort of pinky colours or decreased in the greeny colours. I can talk about how this is actually quantified later if anyone's interested. But you can see that with the same climate projection, under this scenario we see many more countries which are seeing an increase in water insecurity. Under this one, we're seeing many more countries with a decrease in water insecurity. So how the human world plays out is a crucial factor in whether there's enough water to go around, basically. But as I mentioned, there's still a lack of joined-up thinking in this, and I wanted to sort of highlight this because one of the key things about these SSPs, the shared socioeconomic pathways, are they ignore the effects of climate change back on people. They're looking at the human futures, ignoring our impact on climate and its feedback on ourselves. And one key thing is we need to ask the question, if the world's getting warmer, could it actually get too hot for us in some places? I mean, I think this is a fairly logical question to ask and to answer. If the world's getting warmer, we're mammals, we've evolved within a certain range of temperatures. Sooner or later, we will reach a point where it is too hot, surely. So is that point within reach this century? One thing we need to consider in this is the role of humidity as well as temperature. A wet heat is more uncomfortable than a dry heat because you can't sweat and cool your body temperature. So that's the key thing to look at when we're figuring out this question. And there's actually very well-established metrics for this. There's something called wet bulb globe temperature, which combines the temperature and a measure of humidity and solar radiation. And used in many industries, this one is the example used from the US military. So these numbers show when wet bulb globe temperature is at 32 Celsius, then physical training and strenuous exercise is banned. You do get soldiers dying in training under high heat stress conditions. So they're very careful about this. And this gives you a nice standard way of looking at heat stress under future climate change. And we can use the kind of models I showed earlier to look at what a warming world might mean in terms of wet bulb globe temperature and heat stress. And at the present day, we do see some times of the year when some parts of the tropics reach the high 20s in terms of wet bulb globe temperature. So high risk, but not at the extreme risk. This is at the present day. If we roll forward to a 2-degree global warming world, many of the tropics areas are seeing larger increases in wet bulb globe temperature and going into these extreme risk categories in parts of North Africa and the Indian subcontinent. But if we go to a 4-degree world, we're seeing in the hottest month of the year, all of the tropics and some of the subtropics are experiencing these extreme risks of heat stress. So I think we need to ask the question, is that compatible with these projections of population that we're talking about? So this is the poorer, higher populated world. This is the richer, less populated world. These people may be able to afford lots of air conditioning, but are they going to be able to go outside and grow crops and build buildings and so on? I don't know. These people, this poorer world, not everyone is going to be able to afford air conditioning. I think there's important questions about, will the tropics literally remain habitable or not? I don't know the answer to that, so I suggest we discuss it in the coffee break, but I think it's a key question that needs to be addressed. Thank you.
Thank you very much, Richard. We're almost to time, but I'll have time for maybe one quick question. Gaia.
Hi, thanks, great talk. I was wondering, how close are we to understanding, in a wetter world, how much albedo effect of clouds versus global greenhouse gas of water vapour will affect the temperature and so on, and how the feedbacks will continue to sort of affect the precipitation?
All right, great question. And that actually is at the heart of part of what Peter was talking about. One of the biggest uncertainties in the climate sensitivity is the role of clouds and water vapour. I think we're still a long way from really narrowing down the answer, to be honest. There's still a wide range of possibilities about how cloud feedbacks could affect the cooling or the warming of the atmosphere. So not very close, I guess, is the succinct answer, I'm afraid. Sorry.
I think we should close by thanking Richard and all the speakers for a fascinating morning.